finish this little warm-up here, we'll go from current slide. If we'll go to the current slide, there we go. And that's where we'll begin. But in response to your question or comment there about not having left, you're absolutely right. We have class today. We have class Wednesday, but we also have class next Monday. They published this final exam schedule, and I didn't really pay close attention at first, but when I did pay close attention, I saw they had us having final exams on the last day of class. So I emailed the dean to let her know this was incorrect according to the academic calendar, according to administrative calendar, according to every calendar I had seen. And I know she was on the calendar committee when we talked about this, and we set it up this way, and she still put it this way. So I asked my boss, who's the associate dean, Friday when I was over there Friday on the Birmingham West campus. He said, yeah, she realized she did it wrong, but since she already put it out there, she's going to let all the instructors decide what they're going to do. So I talked with one of my instructors this morning, came to this is where I've got stuff to cover. I said, no. I talked with Dr. Pruitt, and here's what he said, that it technically is not supposed to be until the following Monday, but if you saw this and want to go and give it, you can. So she said, no, I've got to cover more material. So now, you're not graduating this term. If anyone listening to this is graduating this term, be sure to let me know, because graduates, I have to have your grades in by Friday at noon, whereas everybody else is the following Wednesday at noon. Now, that's not this Friday, it's the Friday of finals. Okay, now, so we do have class today, Wednesday, and Monday. And on Monday, I'll give you your final exam. And for those who aren't graduating, you have until the following Monday to turn it in. For those who are graduating, you have until Thursday to turn it in, because I have to get grades in by noon on Friday. Okay, so that's the major announcement there. Now, what does that impact? How does that impact us? Well, we're in 12.4 right now, and we're going to finish 12.4 hopefully today. I think we can. And then we'll do a little bit on arc length and curvature. It's not it is a long section, but we'll at least get going on that. But then the last bit of time, I want to at least show you how to do partial derivatives and multiple integration. They're both pretty simple, but I'm going to cut through all the theory and all the other mess and just show you how to do it, because those are things you probably will need to know in the future that we should have gotten to in this class, because we got started. Everybody came in at different levels and places from the previous classes that I tried to bring everyone along together, and it's just taken a lot longer. And then we lost a day last month, a worthless day to go down to Montgomery, and then of course we lost the Martin Luther King Day at the beginning of the term, so we just lost, there was a whole week gone right there, and so starting at the wrong place, so it's eating up our time, and I probably haven't gone as fast as I should have, but with fairly spotty attendance like today, it's hard to go too fast. Okay, so here's example 2. Any questions before we get started? All right. Here's example 2. We had just talked about the tangent line to a curve is at a point, is the line that passes through that point and is parallel to the unit tangent vector. Of course, that's what a tangent line is. Okay? In example 2, the unit tangent vector is used to find the tangent line at a point on the helix. So that's what we're doing today, and this is where it picks up. Find the unit tangent vector, and then find the set of parametric equations for the tangent line to the helix given by this vector equation. R of t is equal to 2 cosine ti plus 2 sine tj plus tk, and we're going to find that both the unit tangent vector, and we'll find that for any point on the curve, t of t, and then we'll find the parametric equations for the tangent line to the helix at the point root 2 pi fourths. Now, get my pen set up first. Now, I think it's a very good idea to make sure that this point is on the curve. I think that would be nice to know, wouldn't it? So, it's going to be a little hard starting with this one or this one, but this is a piece of cake. If t, the last component here is t, and when t is equal to pi fourths, okay, then cosine of t, cosine of pi fourths is
2 squared over 2.
root 2 over 2. And multiply that by 2, and it's just root 2. And sine of pi fourths is also root 2 over 2. Multiply that by 2, and you got root 2. So yes, this point should be on that curve, because the three parameters all fit, and that point should be on the curve. All right, so that's done. That's nothing about what we have to do. How do we go about finding the unit tangent vector? There's something we've got to find first. Yeah, take a derivative, which will be the velocity vector, if you want to call it that. This doesn't have to be motion, but it corresponds with that. So r prime of t. And what would that be then?
Negative 2 sine ti.
Okay.
Cosine, plus 2 cosine tj.
Got it.
Plus k.
Plus k. Got it. Okay. Now that is the derivative vector, which is the unit, which is the a tangent vector at any point there. Okay? But it's not a unit tangent vector. How do we make it a unit tangent vector?
So we put the derivative over the absolute value?
Yes, so the magnitude. Okay? So, sorry. All right. Okay, so it'll be minus 2 sine ti plus 2 cosine tj plus k, and then what would be its magnitude? It's the square root of the component squared. Remember?
Yes, sir.
Okay. So this would be the square root of a negative 2 sine t squared plus a 2 cosine t squared plus 1. Squared is 1. Okay? Okay? Let's just play around with the denominator a little bit before I don't just want to write that numerator over and over again. It's not bad, but it's just a little miserable. So let's just do a little bit here. Okay? Well, 2 sine t squared would be, or negative 2 sine t squared would be sine squared t plus 4 cosine squared t plus 1. Okay, that was easy. Well, let's continue playing around with this sum, especially those first two terms. If you were to add those together, group those together, what could you take out? 4. So that would be the square root of 4 times sine squared t plus cosine squared t, right? Plus 1. And what's sine squared t plus cosine squared t? 1. So that'd be 4 plus 1, it's root 5. So this whole denominator is root 5. That's the magnitude of that denominator. Okay? Now, so I'm going to rewrite this, and there's a couple ways you could rewrite it. I think I'll just do it this way. Minus 2 over root 5 sine ti plus 2 over root 5 cosine tj plus 1 over root 5 k. Okay. To me, that's just about as simple as anything to do that. That's the unit tangent vector anywhere. Okay? But, so we've done the first. Find t of t. There it is. Unit tangent vector at any point. It says, then find a set of parametric equations for the tangent line to the helix given by that equation, the one we've been using, okay, at that point, okay? Now, one thing I can't quite figure out here is, did they really want t of t, which we've gotten for them, we just needed to do that. I think that's what the, because they say, and then find the set of parametric equations for the tangent line to the point given by this at this point. So I think the second part here is find the set of parametric equations for the tangent line to the helix given this at that point. So the second part is not with t's in it, but the ones that will be at that point. Now, that's the part that you sort of have to drop back and remember what those parametric equations were like. And I think this goes back to chapter 11, but let me just for a moment look at see if I can find it real quickly here. I don't do anything very quickly. It may even be 10. Because that's where we talk about parametric equations.
11.5.
11.5, okay.
Parametric equations, the lines are 2 points.
Yeah, okay. So 11.5. That's where I was thinking it was, but I couldn't remember if we needed to actually go back further than that. But that's good if you found that. Okay. Okay. All right, we have the vector, this unit tangent vector, with its 3 components here. So we're looking for a line that's parallel to this vector, passes through this point, okay? So here would be your parametric equations. Let me... All right. So your x is equal to your x1 here, which is root 2. Okay. Plus, now your a is your component of your tangent vector. So that will actually be a minus here. Okay. Minus 2 over root 5 sine t. Okay. Your y will be root 2, second root 2 here, plus 2 over root 5 cosine t, and your z would be pi fourths plus 1 over root 5. That's just a number. It's not got a parameter in it, because that's a number, this is a number. Okay. All right. I think that's the, that should be what they're looking for here. So let's turn back and see if indeed that's what we've got. Now they wrote theirs, and I thought they might, but I was trying to sort of look ahead and see what we needed, and I thought this form was probably a little bit better. Here's how they wrote their unit tangent vector. Well, same thing we did. They just did 1 over root 5, and then they did sine ti, or minus sine ti, plus 2 cosine, oh wait, this is 2 sine, 1 over root 5 times 2 sine ti plus 2 cosine tj plus k. Now that's how they wrote theirs, just so you can see it's the same. They just factored out the 1 over root 5 and then just wrote that one. That's the unit tangent vector with the 1 over root 5 out in front. Okay? And now you see it just like it is in the book. Okay? Now, okay, and this is the part I couldn't tell. It said find the unit tangent vector, and it says, and then find the set of parametric equations for the tangent line for the helix given by blah, blah, blah. So what I did was do that and then get the parametric equation. Then I was going to plug in the value t equal pi fourths, because that we can tell from that point. What they did is not mess with, well, no, they did. No, they've got these same two. Root 2 okay. No, they didn't. Okay. They're finding the unit tangent vector at that point. The way it was worded, I couldn't tell if that's what they wanted, but I guess they did. Find this and that at that point. See, it looked like to me it was find that and then find this at that point. So they want actually a unit tangent vector at that point. So if you wanted to, you could just plug in t equal pi fourths here, and you would have it. And that's why I like my form better than theirs. This would be minus 2 over root 5, and what's the sign of pi fourths? Root 2 over 2, so that basically makes this a root. The 2's would cancel out, and that'd just be a root 2.
How did we put in pi over 4 now?
Okay, because you see at this point here, t is pi fourths. That's how we knew that's the value of t, because it's this function at this point. Well, the t is just the coefficient of your, or the coordinate of your k vector. That's the pi fourths. So you know pi is pi fourths there. So if it's pi fourths there, it's got to be in the other two places as well. So this would be root 2 over root 5i minus root 2 over root 5i. This would be plus 2 over root 2 over root 5, because cosine is also root 2 over 2. The 2's would cancel out and just leave a root 2 over j. And this would be plus 1 over root 5 k. Okay, now, I really don't like writing them like that. I think I would prefer it root the square root of 2/5, the square root of 2/5, and square root of 1/5, you could say. Doesn't really matter, but those are that. Okay. So then, rather than your parametric equation, you see these to be parametric equation, you got to have those t's in there. Well, they trying to see what they've done here. All right, so they're sort of ignoring the root 5 in the denominator, which is okay because it's everywhere in all of those. So they're just taking what they call the direction numbers is the minus root 2i plus root 2j plus 1k plus k. It doesn't quite seem fair. Okay, this is the unit vector there. But if you just take the direction without the unit vector, in other words, exactly what you would get here if you plugged in here, this would give you root 2i minus root 2i plus root 2j plus k. Okay, so either one of those will work. That's the direction, and so the simplest will work as well as putting root 5s in the denominator. So in any ways, those are the slopes, and these are the constants. So again, if you go back to where we were, where was it? 11.5. There it is. All you need, the A, B, and C, are what they call the direction numbers. And they can be any multiple of those. So in our case, it's root 2, 1. That's the simplest. What you get when you plug in t is equal to pi fourths here, this becomes a root 2, 1. Okay? You plug in, you normalize it, then you wind up with that in the denominator. But you don't really need that. Okay? Unit tangent vector needs it. Okay? That's the unit tangent vector. But you could just use the this part, which is root 2, and 1. And that's what they use here, pretty much, as being your direction vectors, okay? The direction components of that vector. Just the coefficients you get from here, without normalizing and making them unit vectors. And that'd be root 2, 1, okay, without dividing by root 5. So from that, this is perfectly correct too, but they can do root 2 minus root 2, I can't write. And then they put, rather than parameter t, they use the parameter s. And I don't like writing an s after a root because it's hard to tell whether the square root ends before or after the s. So I like to put it in front. And this would be, sorry, root 2 plus root 2s. And this one would be, remember we're forgetting about the root 5s, pi fourths plus s. Okay? Those are the parametric equations they use, which is just as good, no different. We use sine t, but that's really more than you need. Just a t alone would work, except I wouldn't want to use t because we use t up here. So that's why they use s instead. And there I put the s afterwards, but I made it really clear. that it was outside. It says that's how the book does it. I guess I should do it that way too. I'm losing way too much here. Okay. That S is outside the radical. That's why I like to write it S root 2 and minus S root 2 and plus S root 2. The book doesn't do it that way. And then that would be just plus the 1 times S. See, those are the direction vectors, is what we call it, root 2, 1. Okay. Without having to divide by root 5. Okay, so those are their parametric vectors. They work. I mean, if you'll notice it said, and a set of parametric equations. You could have lots of other things in there too. Okay, but that's probably the simplest set. Okay, pi fourths plus S, right? Now, okay, so there we found T of T. That's this answer, or this one when they factor it out. Okay. And a set of parametric equations for the tangent line to the helix given by that. And what we did was take any direction vector, the simplest being root 2, 1, okay, and plugging and using this point, and that gave you there, this equation, these equations here, these four here. Okay, and a set of parametric equations for the tangent line to the, yeah, so that's it. That's really all you have to do. Those are the equations for that. Again, you could have these things divided by root 5. They do just as well, but it's just extra writing. So they just lift up them like this. Okay. All right. But they mention at the bottom then, oh, let's go on and see how they did it. So, because I did a lot of, I was making some assumptions, some of them may not have been right. The derivative of R of t, that's the first thing we did, is minus 2 sine t I plus 2 cosine t j plus k, which implies that the magnitude of that is root 5. So therefore the unit tangent vector is that derivative vector, okay, divided by its magnitude, which would be 1 over root 5 times minus 2 sine t I plus 2 cosine t j plus k. There's a unit tangent vector. Okay. At that point, the unit tangent vector then becomes, and here they put 2 times root 2 over 2. Of course, those root 2's cancel out. And let's see how they finally write it. 1 over root 5 times minus root 2i plus root 2j plus k. Now, your direction vector, you can use the point 1 over root 5 or not. Okay? See, now, I couldn't tell from the problem they really want us to do the unit tangent vector at that point. They did want us to. And once they did, there it is. But to do the next step, you don't need the 1 over root 5. You just need those direction numbers, minus root 2, and 1. Okay? And that's what they do. Using the direction numbers, A is equal to minus root 2, B is equal to positive root 2, and C is equal to 1. And the point, x1, y1, z1, which is root 2, pi fourths. Now, it's just bizarre and a little unusual that these are so similar. They're not the same. This is a minus, that's a plus. These are both pluses, and then these are completely different numbers. But even that they're that similar, it's just happenstance of this problem. You can obtain the parametric equations given with the parameter s. Usually they use t, but since we've already used t at the first of the problem, let's just use s here, and then this would be x1, which is your root 2, that root 2, the one in the parentheses there, plus a times, or your a is minus root 2 s. So this will be root 2 minus root 2s. That s is outside the radical. Pretty clear there. The y is y1 plus bs, not the normal bs, but whatever. Okay, and that would be root 2 plus root 2s, and then the z would be the pi fourths plus s, and that's what you get here. So those are the parametric equations that for any line that is tangent to the point at that point. How you know it's at that point? Because when s is 0, you are at that point right there. When s is minus 1, you're on this side, and plus 1, you're on that side. Okay. Well, and this is spatial, so which side we're talking about. So here is the figure. Thank you for drawing it. I didn't want to draw this. Never wanted to draw this. Here is the helix. Now, why they put the gold surface under there, I'm not sure, okay? I guess just to help you see it a little bit better, to see this is what's winding around. But all we're interested in is the black line at the top. See, it's coming around, coming back out, going back in, coming back out. It just keeps going upward, okay? Now, the tangent line at this point, when t is equal to pi fourths, is root 2, root 2 pi fourths. No, at that point, yeah. I'm beginning to have a serious doubt there. Oh yeah, this is your R of t, and it was 2 cosine ti plus 2 sine tj plus tk, and at that point it's root 2, 4. That's the point of tangency that we're interested in. When t is equal to pi fourths, your cosine is pi fourths, is root 2, your sine is root 2, and your it's 2 cosine, 2 sine, and t is pi fourths. So that is the point there. And the tangent line is in the direction of your first derivative vector, which of course is in the direction of your unit tangent vector. But all you need is there's the curve up there. All you need is parametric equations, the simplest one, which would be parallel to minus root 2, and 1. I think that was it. Okay. In that example, there are infinitely many vectors that are orthogonal to the unit tangent vector, orthogonal to the unit tangent vector. One of these is your first derivative of the unit tangent vector. Okay. Now let's go back. Now, we're saying there are an infinite number of vectors that are orthogonal to this one vector here. That's your tangent line. Okay? Because you can take something that's perpendicular to that and go all the way around the line. All those are perpendicular to it. Okay? Infinite number. Okay? One of those is the vector t prime, the first derivative of your unit tangent vector. Okay? Now, why is that true? Well, if you dotted the unit tangent vector with itself, you have the magnitude of the unit tangent vector squared, but it's a unit vector, so that magnitude is 1. Okay. Now, they say this implies this. How? Okay. It's not real clear. Okay. Unless you think about taking derivative of this. Take the derivative of that. Well, derivative of this, you know, this thing is 1. So the derivative of that is going to be 0. Well, what is the derivative of that? Derivative of dot product is the first times dotted with the derivative of the second, plus the second dotted with the derivative of the first. Well, those are twice this dotted with its derivative, right? And if you know that's equal to 0, well, 2 is not equal to 0, so then obviously that has to be equal to 0. So that's how they got there. It wasn't, to me, intuitively obvious how they did that, except if you take the derivative of this thing, and this is equal to 1, the derivative of this has got to be 0. What is the derivative of this? It's the first time derivative of the second plus the second time derivative of the first. That's twice this time derivative of that. And twice that equals 0, and 2 can't be 0, so therefore that's got to be 0. By normalizing the vector t prime, you obtain a special vector called the, oh, by the way, what do they mean by normalizing? They sort of threw the word in here, and it has this meaning, but I don't recall that they told us what it means.
I know what it is for metal.
Huh?
I know what it means for steel.
What does that mean?
It means to bring it to its, if it's supposed to be, it's like 4140, it's supposed to be hard, but you can soften it up to machine it, but then you normalize it, which is bringing it back up to its hardness.
Bring it back up what?
To its hardness that like 4140 is supposed to.
Okay. That may have some bearing on this in that you're making it a unit vector. Normalizing it means bring it back to being a unit vector. So the normalizing this means dividing by its magnitude. Okay? You obtain a special vector called the principal unit normal vector. Okay? Indicated by this definition. Here it is, right here. We just seen that the first derivative of the unit tangent vector. Unit tangent vector is already a vector, okay? A unit vector. Its derivative is not necessarily a unit vector, okay? And the dot product of those is 0, meaning they've got to be perpendicular. So the unit normal vector is the vector in the direction of the derivative of the unit tangent vector, the unit vector in that direction. So you just take it and divide it by its magnitude. And it looks like the same thing, but it's not. Previously, it was r prime over r magnitude of r prime. Now it's t prime over magnitude of t prime. Okay? So let C be a smooth curve represented by r on an open interval. If t prime of t is not equal to 0, good thing for it not to be, then the principal unit normal vector is this. Now, a couple of words here. Principal meaning the one that's positive, pointing inward. The unit means you divide it by its magnitude. Normal means it's perpendicular to the unit tangent vector. Okay. So that's what all those mean. Normalizing it, though, meant making it a unit vector. Yeah, the words all sound so much alike, but slightly different meanings. So here we're going to find the principal unit normal vector. Find n and n of t and n of 1 for the curve represented by r of t. Okay, and this r of t is 3ti plus 2t squared j. So what you reckon we're going to do first? What's the Jesus answer? Take a derivative. All right. We're going to do r prime of t. I have to be careful with that one because in my first class, Cal 1 class, 10 o'clock this morning, I have a pastor and his son in the class, so I have to be careful about using the Jesus, though I think he understands. Okay. Anyway, what is the r prime of t? Got it?
Plus 4TJ.
Perfect. Okay. Now what do you do with that? Why did you do that anyway? What do you want to get out of that?
We are going to find T of T.
Well, first T. Yeah, T of T. You're right. Okay. I was thinking you meant T times T, but T of T. Right. Okay. The unit normal vector, unit tangent vector, which would be?
So that would be 3I plus 4TJ.
Right.
Plus 4TJ, and that's going to be over the square root of 3 squared plus 4T squared.
Perfect. And that would be 3 squared is 9, and 4t squared would be 16t squared, right? Okay. Now, this is a mess. I'm going to, I don't know if this will help or not, but 3 over the square root of 9 plus 16t squared I plus 4t over the square root of 9 plus 16t squared j. Okay. I don't know if that's helpful to write that way or not. I really wanted to do a 1 over 9 square root of 9 plus 16 t squared times 3i plus 4tj. Okay, that would be the easiest way, but just for now, let's do it like that. Okay? But guess what we got to do next?
Oh, we got to take a derivative.
You got to take a derivative of that. So now, here is where I run into problems. Okay? It is a unit tangent vector, but its derivative is not a unit vector, so I go back to putting an arrow over that. Okay? Because t prime is not a unit vector. T was a unit vector, and I'm doing the derivative of the unit vector, but I want to emphasize it's not a unit vector, so I'll go back to putting an arrow over it. Of course, in the book, you just bold and you don't care which is unit or not, but okay. So we got to take a derivative of that. Oh, joy. Now, here's what I'm going to do. Sorry, I've got the yawnies now for some reason. I'm going to rewrite this as 3 times 9 plus 16t squared to the minus 1 I plus 9t. No, that's a 4t. I can't read my own writing. That's ugly, isn't it? So let's clean that up some. 4t times 9 plus 16t squared to the minus 1 j. Okay? Because I like taking derivatives of exponents far better than I do taking derivatives of radicals. Okay? It's a pain in the neck. So let's do our derivative based on that. Okay? Well, to begin with the I component, the only place that t exists is in that parentheses, so 3 is just a constant. And we do a minus 1 times this, so that's going to be a minus 3. 9 plus 16t squared to the minus 2, because you're taking derivative, you subtract 1, right? But then you've got a chain rule, and the chain rule gives you a well, it's a 32t, right?
Oh, right.
Okay. but when you multiply that by a negative 3, that gives you a minus 96 t over the square root no. I kind of messed that up, didn't I? This is to the negative 1/2. Yeah, get out of there. This is negative 1/2, not negative 1. Duh. Okay, so let's back off a minute here. Let's, in fact, start over. Yeah, why don't you say something? Okay. Goodness gracious, this thing keeps interjecting stuff. Okay, let's go back. That's to the minus 1/2. Both of those are. Okay. So, it was a 3, and we know it's going to be times a minus 1/2, and here's Vince. Okay. Now let me go back through a couple of things first. Not going to do everything, but the main thing is we have class today, we have class Wednesday, we have class next Monday. That exam schedule they put out was wrong. Exams don't start until Tuesday of next week, not Monday. So we do have class on Monday. Are you graduating this term? No. Okay. So on Monday, I will have class, and then I'll give you your final exam, which by definition is your last exam, which will be basically chapter 14. Now, in between now and then, we hope to finish 14. I don't know if we'll finish it or not, but we'll get as far as we can. But I do want to give you at least some practice in doing partial derivatives and multiple integration. Those are the two things we didn't get to in this class we should have. I want to at least expose you to that. Okay? They're pretty easy concepts. If we had to go through all the theory and the limits and all that kind of stuff, it drags it out big time. So I'm just going to cut to the chase and show you how to take them. Okay? So that's what we'll do. That may all be next Monday. Okay? Now let me back off and say this too. I'm preaching to the choir here, but I'm talking to the people who aren't here. That means I have to have all of the tests in by, which right now is just two tests completed and in by Monday, because on Monday I will be returning all those tests to you. I would have returned them already, except at both tests there's at least one person who hasn't turned them in. So I have to have those in. And they keep coming.
On the survey, do we have to do it on the maintenance part?
Okay, wait just a second. Let me mark Ryan here. Okay, what was your question?
On the survey, do we have to do the maintenance survey too?
Okay. Now you're talking about student course evaluation. Well, I'm glad you brought up. I forgot to say that to my first class this morning again, so I got to mention that in the future. On your student course evaluation, thanks for saying that. Yes, please do whatever they ask for. One part is, of course, the evaluation of this course, but they've randomly assigned different classes to cover different other areas of the college. You see, for me, I get feedback from you every day, either by what you answer, what you say, questions you ask, or whatever. I get that feedback. So I have a pretty good idea of where you are, what you're doing and stuff, and I see your tests and things like this. The rest of the campus, unless you say something to somebody, they don't get your feedback. So this is the way they can understand how they're being perceived by the students here. Okay, so yes, please do those. Those are important too. I really want mine, but they want theirs too. So please do all they ask for. They're pretty short and simple, aren't they? So yeah.
53 questions.
What's that?
It's 53.
Is that on student course or on the other part?
I'm doing the Cal 3 one right now. It's got 53.
Right, but that's on this course part.
Oh yeah.
But the part on
the search, like for the
yeah,
I don't know how
maintenance, I doubt if it's going to be more than 10 questions. It may be, but it's not going to take you long at all. So please do them both. Please do everything they ask for. Okay. So get back before you came in, and I'll go and repeat that. We got class today, Wednesday, and the following Monday, 1 week from today. We have class. They published a final exam schedule, which was wrong, that said final exams start next Monday. But according to the academic calendar, the administrative calendar, and every other calendar that's been published, final exams don't start until Tuesday. So rather than make one little correction on that, the dean said, well, this will just allow the instructors to give it either day they want to. Well, since I'm not giving, you don't have a sit-down in class final, it's a take-home. We're having class when we're supposed to on Monday, and then I'll give you the final, the last test, which will be basically Chapter 14 test. Okay, but between now and then, either today, Monday, probably not today, Wednesday or Monday, I'm going to go over with you how to do partial derivatives and how to do multiple integrations. It's really pretty simple. If we did all the theory behind it and all the limits and all that kind of stuff, it takes a long time to do it. I'm just going to show you how to do it, which is all you're ever going to need. You're engineering, right? Pre-engineering? That's all any of you are going to need. If you get into theoretical mathematics, you might need the theory. You can read the book. Okay. All right. So anyway, that's how we're going to wrap up. And are you graduating this term?
I'm a transient student, so.
Oh, you're a transient student. Okay, yeah. So you don't have to worry about it. Okay, so your grades will be, if you were graduating this term from Lawson, that meant that I have to have your grades in by 12 o'clock noon, not this Friday, but next Friday. But if you're not graduating this time, transient or a regular student here, then the grades are due in by noon Wednesday the following week. So that's when your grade, I'll probably have them in sooner than that. Depends on when you get me your finals in, then that will be what it depends on. But I have to, the point being, if you were graduating this term, I have to have your final in by Thursday. I'll give it to you Monday. I have to have it in by Thursday. If you're not graduating this term, which sounds like all three of you, then that means you got until the following Monday to get it back to me, because I have to have your grades in by the following Wednesday at noon. So that's that. Okay. Now, back to where we were here. We're finding the principal unit normal vector for this position function. R of t is equal to 3t I plus 2t squared j. Okay. Now, what we're doing, first thing you have to do is take the derivative of that, and that gives you 3i plus 4tj. Then you have to normalize that to get it to be a unit tangent vector. So you put that vector, the r prime, in the numerator, and then the derivative of the magnitude of that in the denominator, which is the square root of 3 squared plus 4t squared. So that's the square root of 9 plus 16t squared. And so you can write it like this. But I said I preferred to write it like this, which is 3 times 9 plus 16t squared to the minus 1/2. That brings it upstairs and gets it in power form. Plus 4t, that's the numerator here, times that same denominator, 9 plus 16t squared to the minus 1/2. And then we started taking the derivative of that vector, okay? That's what we had just started when I found out I made a mistake, so I went back to start it over again. So, we got the 3 that was there, I got that far. But we're also going to have the parenthetical part to the minus 1/2, so that's going to be minus 3/2. The 3 from what's in front and the minus 1/2 from the exponent. Times 9 plus 16t squared to the minus 3/2. When you take a derivative, subtract 1. But then you've got a chain rule. And the chain rule gives us another 16t, right? No, 32t, sorry, 32t. So I'm going to multiply this by 32t. And if you don't mind, I'm going to do it this way. That was a minus 3/2 times the 32t. Okay? Right. Well, 2 will go into 32 16 times. That's a minus 48t is what that turns out. Just hang on to that. We'll come back to it. Okay, and that's all I. Okay? Now, the J part. We got a product rule on this one. The I part was just a 3 times that. The J part has 3t times that. So we're going to have to do the same type thing, but we got to do it with a product rule. Okay, do you remember how that goes?
First times the derivative of the second.
Okay, so it will be a 4t times the derivative of the second. Now, we've just done the derivative of the second. That was I thought I'd left enough room, but I'm thinking I didn't. Okay, or I left it in the wrong place. Okay, so that's going to be a 4t times a minus 1/2. So that's going to make this a minus 2 minus 2t. Okay. All right. Times 9 plus 16 t squared to the minus 3/2. Then the chain rule is going to be an additional 32t. Just like before. Still didn't leave enough room for it. But that's just the first part, okay? So I think what I'll do, goodness gracious, this thing is messy. Okay. All right. I'll come back and clean that up a little bit. The second part of your product rule is plus. Remember, there was originally a plus in front. Plus the second times the derivative of the first. What's the derivative of the first? 4. So that would be 4. Now, I'm real tempted to put that over because I think we'll want it down there. The square root of 9 plus 16t squared. Okay. And maybe I should have left the plus there. All this is time j. Okay? Oh, what a tangled web. Now, that's your t prime of t. Okay. Now, before you normalize that, okay? Oh, no, we've got to, don't we? Man, this is a pain in the neck. Okay. All right, just see what we've got here. Your t prime of t all right. Now notice what they did. They've got the 16t with the minus sign here over 9 plus 16t squared to the 3/2 power. When they put it downstairs, that makes it there. And then they have the 3 with the I, and they have that same kind of term here, only it's a 4t, because they're going to factor out the 16 only, and they had a 32 here. Factor out a 16, that leaves a 2 t there. Factor out 16t, and that leaves them a 4t there. And then the other part was this one here. They've got the 4 with the j and 1 over 9 plus 16t squared. So they wrote it really, really differently. Okay? And then their next step is really bizarre. So I'm going to try to reproduce what they have, but I'm going to try to do it a little simpler than, well, I don't know if it's going to be simpler. Okay, so what they're pulling out of everything here, or not quite everything. Yeah. Okay. So, just trying to get it into their form is the hard part. All right. So we've got a 16T. That's there. Over 9 plus 16T squared to the 3/2 power. Okay. Here's the 16T here, and there's the denominator there. Okay? And that's times a minus 3I. Now this is a weird way to do it, but it's how they're doing it, and it's okay. Okay? I'm just trying to make mine look like theirs. Okay? Only they put the minus here, sorry. Let's put the minus here and make that the plus. Okay. Now, I think we got it the same as they do. Okay? Now, the next term here is a is also a minus 16T. Okay. Now I know it only says a 30. There's a minus here. That's fine. And here's a 2T and a 32T. I'm only going to take out the 16T just to make it look like that one. But remember, those are there. This is also over 9 plus 16T squared to the 3/2 power. Okay? So we got both of those terms being the same, but this is times a J. I already got the minus out there, so what you have here is plus. Remember, we took out 16T. That left a 4T here. So it's 4TJ. Okay. You with me there? Not really. Okay. Okay. I'm trying to do it the same way they did. They pulled out only a minus 16T here, and that they got from 2 will go into 32, 16. So that's a minus 16T here, leaving the 3 with the I. Okay? And then the rest of it's over this. Because that's to the minus 3/2, put it in the denominator. That's a 3/2. I don't know what it looks like from where you sit. From here, it doesn't look like a 2. So let me make that look more like a 2. That's what it was, but it just came out really ugly. 3/2. That's still probably pretty ugly. Okay, we want that same factor here. Well, here we have a minus 64T squared. But we want only a minus 16T here. So we want the minus 16T here. That left us a 4T here. 2 from here and 2T from there. So those are going to join the J here. Okay? And we put this over that. So these two coefficients are exactly the same. Okay. Now, the part that's missing is this last part, and that is a plus now, not a minus. Plus, and let me get this the same way they have theirs. Yeah. Oh my word. Where did they get this? 16T. 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 Oh, I see, yeah. Yeah. 1 over the square root of 9 plus 16. Why they went to square roots here, I'm not sure. They should have left it to the 1/2, but I'm trying to do it the same way they did. T squared. And this then is the coefficient of 4j. They brought the 4 out with the j. Don't ask me why. Okay. Now. Okay. You okay with that? You see, this is exactly this term here is plus 1. They put the 4 out here with the j over this. All right. Now, all these two denominators are to the 3/2, that's to the 1/2. Least common denominator is the 3/2. So that means we're going to have to multiply this by 2/2, which means in the numerator it's a 9 plus 16t squared. Okay, you buy that? So let's write this as 9 plus 16t squared, and then we'll make this to the 3/2 as well. Now we have same denominators. Okay. Now, and I put an extra set of parentheses, or at least half of one here. I'm going to take it out for now. Okay. Okay. I think that's okay. Now we have same denominators. This is one weird way to go about doing this. So let's get our i's here. They leave the 3i out there. I don't know why. No, they don't. Yuck. Okay. I'm trying to help you rationalize this, and it is not easy. Okay. If you for the life of me, it looks like they reversed their. No. Let's just do it. Okay. This is going to be, I'm not going to follow the way they do it anymore. Up to now, we're on the same page. So let's see how they're going to do it here. This is minus 16t times the 3. That's minus 48t over this denominator. I'm not going to write it every time. And that's times I. Okay? And then here we've got minus 64t over that denominator, t squared, over that denominator times j. This is minus 16t times a positive 4t, that's minus 64t squared. Okay? J. And here we have a plus 36 over that denominator, j, plus 64 t squared over that denominator, j. Okay. I don't know, I mean, I'm having to simplify things. This we get from minus 16 times 3, minus 48ti over that denominator. Here we get a minus 64t squared over this denominator j from this one. Here we get 9 times 4 is 36 over this denominator j with no t's in it. And this one is a plus 16t squared over this denominator. No, plus 64. 16 times 4 is 64 for that denominator. Well, look at that. This one and this one are exactly the same but opposite sides. So those can go. I'm beginning to wish I'd have done it my way first. Okay, so those are out of there. So now we have no room to write. Okay. Okay. So we have common factors between 48 and 36 are 16, right? So let's factor out a 16 over this denominator, the square, let's just write it as a 9 plus 16 t squared to the 3/2 power, okay? That's common to both of those, okay? And what do we have left with the I? Well, 16 will go into 48t. Actually, let's pull out a t. No. Doesn't have a t with it, okay? That gives us a minus 3t I plus 16 will go in the, is that, it's not a 16. There's Daniel. Yeah, I messed something up. Okay. I was doing those two. 12. It's a 12. So let me clean that up. That's a 12 here. 12 there, and this will be a 4tj. Let me clean that up too. Okay. Whew. Okay. Plus, and that'll be 3. No, this is I. Goodness gracious. J, and this is I. All right, let's see if we got the same thing they did. 12 over 9 plus 16t squared to the 3/2 times a minus 4ti plus 3j. Yes, we got the same thing they did. That is your t prime. Anyone think that might be a unit vector? Guess again. Okay. But how in the world are we going to make that into a unit vector? We're going to need to divide that by its magnitude. Okay? And its magnitude is squaring the first part, because that's multiplied by everything, and squaring the individual parts. Okay? So, and then taking a square root of all that. Boy, what a pain in the neck this is. Okay. Okay. So let me do what they just said. We're going to be, this is the first derivative of the unit tangent vector as a function of time. Okay. And we want its magnitude. So we want the square root of this thing squared. Right? Well, wait. Okay, this part here, leave that out, okay? That is, what we would do with that would be the square and then take a square root of it, which leaves this. So that's going to stay that, exactly that. 12 over 9 plus 16t squared to the 3/2. If you squared it and took a square root of it, you would get that. But here we do have to take the square root of these squared. Now this is a 16t squared plus 9. Hey, we've seen that before, haven't we? Okay? And that just happens to be the same as this, right? So this is to the 1/2, this is the minus 3/2. So 1/2 goes into this, so this is just merely 12 over 9 plus 16t squared. That's it. That's all that's left, okay? And that's what they get here, 12 over 9 plus 16t squared. That is the magnitude, and I wrote this poorly. This ends right here. This part here is the magnitude of t prime. That's what this is. Okay. Yuck. What a pain in the neck this is. So, find the unit normal vector. I'm going to erase just about everything I've got here, unfortunately. These are no trivial problems, as you can guess. Most of the time we don't have this much of a variation in it, this many things to have to deal with. Most of the time they'll give them to us much, much cleaner than this. We want to leave this part, okay? Actually, I have it all up there, so I don't even need that part. So let me go back and erase this too. Well, I thought I was erasing it, but I'm not. Okay, yeah. I hope I'm not erasing too much here. I probably am, but I'm sick of it, so I don't care. Okay, we're running out of time to boot. Okay. Now, there's your t prime right here, and this is your magnitude of t prime right here. Okay? So we put that on top of each other. Okay? Now, the good news is, and this is the unit normal vector, and this is a unit vector of t, and that's the first thing they ask for here. That's equal to this thing, which is 12 over 9 plus 16t squared to the 3/2 power times minus 4ti plus 3j divided by this here, which is 12 times 9 plus 16t squared. Well, look at this. 12s will go out, and this thing will go into that 1/2 times. So the unit normal vector is 1 over the square root of 9 plus 16t squared times minus 4ti plus 3j. Okay. And that's what they get here, 1 over the square root of 9 plus 16t squared times minus 4ti plus 3j. Okay, that's your unit normal vector. That one you could check and make sure that it is a unit vector, and sure enough, it pans out perfectly. Okay. The second part said, though, find n of 1. So the unit normal vector at the point where you are when t is equal to 1, then this is what you would have here. This is 1 over the square root of 9 plus 16, because 1 squared is 1, all right, times minus 4i plus 3j. And does anyone know what the square root of 9 plus 16 is? 5. Okay, so this would be minus 4/5 I plus 3/5 j. And that's real easy to tell that is a unit vector, because you square this, you get 16/5 plus 9/5 is 25. 16 25ths plus 9 25ths is 25 25ths, and that is a unit vector. Okay, so there's your n of 1. They put the 1/5 out front, 1/5 of minus 4i plus 3j. Wow. Now, fortunately, I hope you'll realize most of the time they're not going to be this complicated. Why they decided to launch into this, I'm not sure, but they can be complicated. Okay. Now, here is the, oh, well, they may show that. So let's see how they did it. Sorry about this. Okay. First thing they do is take a derivative. We did that. And take the magnitude of that derivative. We did that. And the unit tangent vector is the first derivative of the displacement vector divided by its magnitude, which is that thing, which is exactly what we got. Okay? Now, differentiate that, and they skipped all kinds of steps here and jumped right to this. Don't think you can do that in one full blast here. Well, maybe they could. Yeah, I guess they could. Just pull out the other thing and take the derivative, and that would give you, maybe they did it a far easier way than I did. So you recombine all those things together and you get that exactly like we did. And then the derivative of that is 9 times, and they wrote it in a really weird way, but it's okay. That's correct. And that just came out being that, which is exactly what we got. Then when you divide those, that gives you unit normal vector, and that gives you that form, which is exactly what we got. Now, when t is equal to 1, then you get this, and here's the graph of this thing. 3ti plus 2t squared j. It is, I guess, sort of like a parabola. Okay? The unit tangent vector is in this direction, unit normal vector in that direction. Why do they call it principal? Because it's always positive. The one that points inward is always positive. The one that pointed outward this way would be exactly the negative of this. So that would be not the principal unit normal vector. Now, there's, like they said at the beginning, there's an infinite number of these normal vectors, but we're staying within the plane. That's the one that's within the plane. Okay? The principal unit normal vector always points to the concave side of the curve, like we just found here. Okay. So, let me point out a couple things to you. There's a unit normal vector. There's the unit tangent vector. Notice the coefficients are exactly the same. 1 over the square root of 9 plus 16t squared. See? But their others have to be perpendicular to each other. And if you'll think about it, this one, 3 plus 4t, 3i plus 4tj is 3i in this direction, 4t is something in that direction. Whereas the other one, and if you did a dot product with that one and this one, 3i plus 4tj, dot product with this, you get a minus 12t here, plus 12t there, it adds to 0. So sure enough, these are perpendicular to each other. Same coefficients. They're unit vectors. Okay, when t is equal to 1, then this becomes 1 over 5 times minus 4i plus 3j. And that's shown there. Whew, goodness gracious. I think I did it a little longer procedure than they did, but they are not usually very simple. All right. This is the top of the next page, page 848. The principal unit normal vector can be difficult to evaluate algebraically. Yes, tell me about it. For plane curves, you can simplify the algebra by finding t of t, that's the unit tangent vector, is equal to x of ti plus y of tj. That's the unit tangent vector. and observing that the unit normal vector must either be switch these two and negate one or the other. Okay? If you switch these two and negate the x, that would be normal to this. Negate the y, and that would be normal to this. Well, one of these is a positive principal and one of them is not. You just have to figure out which one's going in the direction of curvature. And that's what I was pointing out to you before. One of ours was 3i plus 4tj. The other was minus 4ti plus 3j. So they're exactly, you just switch the two and have them in the, but then you just have to figure out which one's pointing in the right direction. Because the square root of that is 1, it follows that n1 of t and n2 of t are normal vectors, unit normal vectors. The principal unit normal vector is one that points to the concave side of the curve, which then means you have to figure out which way it's curving, which is not usually a trivial thing to do, and then pick that as the principal unit normal vector. This also holds for curves in space. Picking the concave side of that, you have to be pretty careful. So that's for an object moving along a curve C in space. Here's your curve C. The vector t of t is, okay, I was going this way, but this happens to be coming this way. So here's your t of t is in this direction. Now, from there, the unit normal vector is in the positive curvature, in the curvature, in the inside of the curve, concave part of the curve. So the t of t is always the direction the object's moving. I was just assuming it was moving this way. It wasn't. It's moving this way. So the t is this way. Unit normal vector is toward the center. Where the vector is orthogonal to t and points in the direction which the object is turning, as shown here. It's turning inward, so that's one. At any point on a curve, the unit normal vector is orthogonal to the unit tangent vector always, and the principal unit normal vector points in the direction in which the curve is turning. See, here it would be pointing this way. Here it would be pointing this way. That one's pointing that way. It's hard to tell here, pointing this way. All right. There is an example 4. They're skipping, so let's see if we can do that quickly. I can't do very much quickly. How much time do we have? We are out of time, aren't we? Okay. So that's where I'm going to have to pick up next time. Let me see. I'll start right there, example 4. Okay, sorry we didn't get any further than we did. Oh my goodness. Oh, goodness gracious. I left my eraser down in my backpack. I didn't do something this morning because I didn't think I had my eraser with me, but I do. Okay. We'll pick up with example 4 next time. So, homework exercises here. We came close to finishing this section, but not quite. Do any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. Any of the odds 9 through 13. They're all at Calc Chat. 9's at Calc View. Any of the odds 15 to 19. They're all at Calc Chat. 15's at Calc View. Do either 21 or 23. They're both at Calc Chat. Any of the odds 25 to 29, they're all at Calc Chat. 27's at Calc View. Either 31 or 33, they're both at Calc Chat. Any of the odds 35 to 39, no, wait. Nope, sorry. Gave you too much. Stop at, I'd say 23. You don't need to do past 23 because the others are tangential and normal components of acceleration, which is the next thing we're going to cover after we do example 4. All right, so Wednesday we'll finish example 12.4 hopefully, and we'll start on 12.5. And then once we've get as far as we can on 12.5, that pretty much will determine what your test will be, but I will take most of next Monday going over how to do partial derivatives and multiple integrations. Those are the other two big topics in Cal 3 that we didn't really get to. They're pretty simple, straightforward. They follow regular derivatives and single integration pretty closely. Just a few little differences of things you have to keep in mind. I'll point those out to you on that next Monday. So we'll get as far as we can next time, hopefully finish 12.4 and maybe get into 12.5. Good deal. Any questions? Sorry, that one example today took way too long.